Download this code from codegive.com, link in the description below. Distributed Systems, the Byzantine Generals Problem, a deep dive. The Byzantine Generals Problem is a classic thought experiment in distributed computing that illustrates the challenges of achieving consensus in a system where some nodes may be faulty or malicious. It highlights the importance of robust consensus algorithms in distributed systems like blockchains, databases, and cloud infrastructure. This tutorial will cover the problem in detail, explore its implications, discuss some potential solutions, and provide a code example illustrating a simplified implementation. 1. Understanding the problem ***. Imagine a group of Byzantine generals surrounding a city they want to conquer. They must agree on a single plan of attack, either attack or retreat. Communication happens only through messengers. However, some of the generals, and even the messengers, could be traitors. These traitors can send contradictory messages, lie about orders, or simply fail to deliver messages, aiming to prevent the loyal generals from reaching a consensus. The problem statement ***. How can the loyal generals ensure that? Agreement, consistency. All loyal generals agree on the same plan of action, attack or retreat. Validity. If the commander, the general issuing the order, is loyal, then all loyal generals follow the commander's order. Key assumptions ***. Communication is point-to-point. Generals send messages directly to each other. Messages can be authenticated. Generals can sign their messages, preventing others from impersonating them. This does not prevent a traitor from sending different signed messages to different generals. Generals know each other. Each general knows the identity of every other general. Unreliable medium. The communication channel, messengers, might be unreliable. Messages might be delayed, lost, or altered by traitors. Binary decision. The generals must decide between two possible actions, attack or retreat. Why is this problem important? The Byzantine generals problem isn't just a theoretical exercise. It directly relates to real-world distributed systems in several ways. Fault tolerance. It models the scenario where some nodes in a distributed system may be faulty or malicious, leading to inconsistencies in data or processing. Distributed consensus. It demonstrates the difficulty of achieving consensus when nodes cannot perfectly trust each other. Data integrity. It emphasizes the need for mechanisms to ensure that data is consistent and reliable across a distributed network. 2. Formalizing the problem, M and N. N. The total number of generals, nodes, in the system. M. The maximum number of traitorous generals. A key result is that consensus can only be guaranteed if N3M. In other words, you need more than 3 times as many loyal generals as traitors. We'll explain why this is crucial later when discussing solutions. 3. The challenge, traitorous actions. The traitorous generals can perform several malicious actions, making consensus extremely difficult. Sending conflicting orders. A traitorous commander can send different orders to different lieutenants. For example, attack to some generals and retreat to others. Lying about received orders. A traitorous lieutenant can lie about the order received from the commander. They can claim to have received attack when they were actually told to retreat, or vice versa. Failing to relay messages. A traitorous general can simply refuse to pass on messages, preventing information from reaching other generals. Colluding. Traitorous generals can coordinate their lies and misinformation to confuse the loyal generals. 4. Visualizing the problem, the cases of 2 and 3 generals. Asterisk case 1, 2 generals, commander and lieutenant. If the commander is the traitor, they can send conflicting orders. If the lieutenant is the traitor, they can lie about the order received. In either case, the loyal general cannot reliably determine the intended action. Asterisk case 2, 3 generals, commander and 2 lieutenants. This is where the N3M rule becomes apparent. Let's say the commander is the traitor. 1. The traitorous commander sends attack to Lieutenant A and retreat to Lieutenant B. 2. A and B exchange the messages they received. 3. If A is loyal, it tells B it received attack. If B is loyal, it tells A it received retreat. Now, each lieutenant faces a dilemma. They know the commander's order might be truthful, but they also know the other lieutenant's report might be truthful. Without more information, they cannot confidently decide on a single course of action. Why N3M is necessary? Asterisk. The N3M rule is fundamental because it ensures that even in the worst-case scenario, the loyal generals will receive more consistent information than misleading information. Let's break down the reasoning. Asterisk. If M traitors exist, asterisk, the most misleading information will come from these M traitors. Asterisk. If N3M, then N, M2M asterisk. This means the number of loyal generals, N, M, is greater than twice the number of traitors, 2M. Therefore, the loyal generals will contribute more accurate information to the overall decision-making process, overwhelming the influence of the traitors. 5. Solutions, algorithms for Byzantine fault tolerance. Several algorithms have been developed to solve the Byzantine generals' problem. These algorithms aim to achieve consensus despite the presence of faulty nodes. A. Lamport, Shostak, and P's algorithm, Practical Byzantine Fault Tolerance, PBFT, is based on this. This is a recursive algorithm that works by having each general broadcast the order they received to all other generals. Generals then use a majority vote rule to decide on the final action. The algorithm is complex but provides a good foundation for understanding Byzantine fault tolerance. Simplified explanation, for understanding, not a fully robust implementation. 1. Commander sends order asterisk. The commander sends an order, attack or retreat, to all lieutenants. 2. Lieutenants relay orders asterisk. Each lieutenant relays the order they received, whether truthful or a lie, to all other lieutenants. 3. Majority vote asterisk. Each lieutenant calculates the most frequent order they received. If a majority of generals voted for attack, the lieutenant chooses attack. If a majority voted for retreat, the lieutenant chooses retreat. Limitations asterisk. Asterisk. Message complexity asterisk. The message complexity grows exponentially with the number of generals, making it impractical for large systems. O.N. This is a significant drawback. Asterisk. Assumes synchronous communication asterisk. It often assumes messages are delivered within a known time bound. This assumption is difficult to maintain in real-world asynchronous networks. B. Practical Byzantine Fault Tolerance, PBFT. PBFT is a more efficient algorithm that is widely used in distributed systems. It uses a series of phases, pre-prepare, prepare, commit, to achieve consensus. It reduces the message complexity compared to the original Lamport algorithm. Simplified explanation asterisk. 1. Request asterisk. The client sends a request to the primary node, leader. 2. Pre-prepare asterisk. The primary node proposes an order/action and sends a pre-prepare message to all other backup nodes. 3. Prepare asterisk. Each backup node validates the pre-prepare message and sends a prepare message to all other nodes, including the primary. 4. Commit asterisk. Each node, primary and backup, that receives a sufficient number of prepare messages, more than 2/3 of the nodes, sends a commit message to all other nodes. 5. Reply *. Once a node receives a sufficient number of commit messages, it executes the action and sends a reply to the client. Key advantages of PBFT *. Improved message complexity *. PBFT has a message complexity of O(n)(2) per consensus round, which is a significant improvement over the original Lamport algorithm. Relatively simple implementation *. While complex, PBFT is more practical to implement than some other Byzantine fault-tolerant algorithms. Widely used PBFT is used in several real-world distributed systems. C. Raft and Paxos *. While not strictly Byzantine fault tolerance algorithms, they handle crash failures better than malicious failures. They are important consensus algorithms. They are often used as building blocks for more complex Byzantine fault-tolerant systems. Raft Raft is easier to understand than Paxos and provides a clear leader election and log replication mechanism. Paxos Paxos is a family of consensus protocols that is known for its theoretical elegance and resilience. D. Federated Byzantine Agreement, FBA. FBA, used in systems like Stellar, focuses on open membership and trust networks. Instead of requiring every node to know about every other node, FBA allows nodes to define their own quorum slices, sets of other nodes that they trust. Consensus is achieved when enough overlapping quorum slices agree. This makes FBA more scalable and flexible for large, open systems. 6. Code example, Simplified Byzantine Generals Problem, Python. This is a very simplified implementation to illustrate the concepts. It's not robust enough for real-world use. It uses a majority vote approach. Explanation of the code *. 1 Byzantine_generals, number_generals, number_traitors, commander_order, *. Takes the number of generals, traitors, and the commander's initial order as input. Checks if N3M condition is met. Initializes a general's dictionary to store information about each general, whether they are a traitor, the order they received, and their final decision. Randomly assigns generals as traitors. 2 Commander's order *. If the commander is a traitor, it sends random orders to the lieutenants. If the commander is loyal, it sends the same order to all lieutenants. 3 Message exchange *. Simulates the exchange of messages between the lieutenants. Traitorous lieutenants lie about the order they received. Loyal lieutenants truthfully relay the order they received. 4 Majority vote *. Each lieutenant calculates the most frequent order they received. The lieutenant chooses the order that received the most votes. If there's a tie, the lieutenant randomly chooses an order. 5 Output *. Prints the final decisions of each general. Checks if consensus was reached, all generals agreed on the same order. Important considerations for real-world systems Authentication in real-world systems, you need strong cryptographic mechanisms, digital signatures, to ensure that messages are authentic and haven't been tampered with. Asynchronous communication Real networks are asynchronous. Algorithms need to be designed to handle delays and message loss. PBFT handles this by using timeouts and resends. Node recovery Distributed systems need mechanisms for nodes to recover from failures, crashes, network partitions, etc. Scalability Algorithms need to be scalable to handle a large number of nodes. FBA attempts to address this with its trust network approach. Complexity Byzantine fault-tolerant algorithms are complex to implement correctly. Careful testing and verification are essential. 7. Conclusion. The Byzantine general's problem is a fundamental challenge in distributed computing. It highlights the difficulty of achieving consensus in the presence of faulty or malicious nodes. While perfect solutions are difficult to achieve, algorithms like PBFT and FBA offer practical approaches for building robust and fault-tolerant distributed systems. Understanding the problem and its solutions is critical for anyone working with distributed databases, blockchains, and other mission-critical distributed applications. Remember that the provided code is a simplified illustration. Real-world implementations require significant engineering effort and careful consideration of the specific application requirements.